Good morning, everyone. Thanks for coming. And there has been two ONNX releases since we last met. The latest one is 112 done by IBM. So let's give it a round of applause. Contributors have made many had added many new features to ONNX and keep making ONNX better. Chip inference has improved at operator level. Contact linear able to handle incorrect, but not missing optional. Error checking for incorrect permutation was added for transpose. Shape inference for constant of shape is simplified, and the shape inference for expand was improved such that symbolic shape is used. Gather and shape are now utilizing result from data propagation. This last improvement was made possible by extending info shape API to expose result from data propagation. It helps PyTorch exporter to utilize the ONNX chip inference functionality. And chip inference for local functions was added in release 1.11 and further enhanced in the latest 1.12 release. Next slide. ONNX generates test data for downstream applications to validate its implementation. In this current release, node test data is generated with a deterministic offset version. By default, the latest synth version is used, and it is possible to select a offset version other than default if needed. And we have updated all the test data with this latest behavior. And because of this deterministic measure, we are able to validate test generation in all CI pipelines. CI systems for Linux release has been changed to many Linux 2014 because an early version is no longer supported. We have dropped the support for x86 32-bit Linux, and the release packages for Python 3.10 were added to the release. We no longer produce packages for Python 3.6. And there are two important releases added. Model Composer can be used to creating and combining models out of several graphs and models. And the Function Builder can be used to construct function operators. It is impossible in this presentation to list all the improvement made by contributors. Here is just a shortened or overly shortened list. Initializers are decoupled with input such that a virtual converter can reliably convert models across any offset versions. And with a few additional bug fix, model converter has become more stable. In the repo, Python code is modernized with type annotation, showing our aim for the highest coding standard. The model parser has been improved to support richer Rama, and there are tons of fixes. In the next, we plan to provide a better support for ONNX releases. We realized that from our experience that the major risk factor for release delay was due to breaking changes that were detected by the runtime while building the release. So to alleviate this, we will plan to provide a CI pipeline for the runtime to automatically detect any breaking changes while doing a release, and so that early action can be taken. And we will also, continue with our focus on shape inference improvement. And last but not least, we will continue to provide the infrastructure and the architecture support for operator data processing and other special interest groups. And thank you.
Hi, I'm Rama, and I'll be presenting the update on behalf of the operator SIG. Since some of you may be new to ONNX, let me give a quick summary of the focus of the operator SIG. The ONNX spec, as Prashant earlier said, breaks into two parts. One is the IR and its semantics, and the second key part is the set of operators that constitute part of the spec. And the operators SIG focus on the second part primarily. And the operators are organized into domains, and there are two domains, the ONNX domain, which focuses on DNN operators, and the ONNX ML domain, which focuses on classical ML operators. And these are versioned, and the SIG mostly focuses on how to evolve this set of operators, adding new operators as needed, and clarifying operator specs, and making changes to them as and when needed. So let me give a quick update on the changes that were introduced in the last two releases. The two new offsets, offset 16 and 17, were introduced in the last two releases. So in terms of the new ops introduced, we have grid sample, which is used in spatial transformer networks, a layer normalization, which is widely used, for example, in language models such as BERT. Signal processing ops, basically DFT or AFFT, they have been widely requested, and they are used in audio models. And sequence map, which was proposed by the pre-processing work group, which enables us, for example, to handle batches of images, for example, of varying sizes, if you want to pre-process them and convert them into a format required for a specific model like ResNet 50. And most of these are functions, except a grid sample and a few others, but there's a plan to promote them to be functions soon. And some of the existing ops were also updated. So, for example, scatter op was updated to allow support for duplicate indices, where you can say the values specified for duplicate indices should be summed up, for example. And support and some of the ops were extended to provide support for types such as bfloat 16 and optional types. And RO align had a minor update to adjust for a variation between different frameworks where the results were different of a pixel. So yeah, let me in the remaining few minutes, let me describe some of the plans going forward. And as I remember, the key goal for the operator SIG is primarily to have a clear and unambiguous specification, and there is room for improvement here, and we do need to improve the documentation for the spec for various ops. And as to the remaining goals, there is really a trade-off here, because on one hand, we would like to have a compact specification that is a smaller set of primitive ops that makes it easier to develop a new backend, for example, on a new hardware, and basically make it much easier to implement ONNX on new settings. On the other hand, we also would like to support the new kinds of models that come along, even support encoding pre-processing and post-processing logic in the model itself. And this leads to a desire to add more ops to the spec, basically. And the desire for efficiency also leads to a desire to add more complex composite ops that are coarse-grained but can be implemented efficiently. So there's a tension here, and we basically need to strike a balance between these two And one of the key techniques we use to deal with this challenge is the notion of ONNX functions. And an ONNX function is essentially an ONNX op whose semantics is specified by in terms of other primitive ops. So effectively, this function definition provides an executable specification for the op, thereby improving the spec clarity, reducing ambiguity. But it also provides a default implementation so that it makes it easy to build a new backend. At the same time, when efficiency demands it, you can build a specialized kernel in specific backends for these ops. So allowing us to balance these conflicting requirements we face. So going forward, one of our goal is to reduce the set of primitive operators, basically by promoting them into functions. So we have identified around 25 to 30 of existing ops that can actually be promoted as functions, and we plan to do that. And one of the interesting new directions we are planning to take is to enable authoring ONNX in Python. So, and have a tool that automatically converts the Python function into an ONNX function proto, which is the serialized IR representation for functions in ONNX. And the plan is to also allow use this as a way to debug using standard Python debugs, for example, the definitions of functions and to understand them. And so the plan is to use a subset of Python we call ONNX script to enable all of this. So let me give some example, a few examples. So here you see a function definition in Python for the well-known Jalu activation function, and so the plan is we define the function in Python this way, and the converter will automatically generate the Jalu function definition. And as you can see in ONNX, the real function definition expands into a lot more operators and is less readable, but the compact specification is easier to author and also to read and understand. So, and so this is another example that illustrates the use of control flow. So, for example, a dropout, which is a standard op in the Python spec, can itself be specified as a function on top of a random uniform generation. And again, the use of control flow makes it, Python control flow makes it easier to naturally and compactly specify the semantics of these ops as a function. And so this just illustrates the use of standard debuggers to understand these function definitions too. So for example here, you have a TIE example Python definition of an ONNX function, and you execute it just like you would execute in a standard Python by creating some inputs and invoking the function. And you can use the debugger to look at the values and understand the spec. So yeah, these are just some more examples for people interested, just to show how various existing ONNX ops can be compactly specified. Yeah, so that brings me to into the end, and thanks for coming, and please do get involved with the operator SIG. As shown here, there's a Slack channel, and we have monthly SIG meetings that you can join, and we welcome your contributions. Thank you.
Okay, great. Yeah, unfortunately, I could not make it to the meeting in person, but it's great to see all the participants here. So my name is Kevin. I've been involved in the ONNX community for the past couple of years, and today I'll be giving an update for the converter SIG and all the work that we've done since the last time we've met. So for the outline of this presentation, I'll be going over the converter update. So first, I'll be going over the front-end converter updates, which mainly deal with DL framework into ONNX model conversion. And for these front-end converters, I'll be going over the PyTorch to ONNX, TensorFlow to ONNX, and sklearn to ONNX converters that we have. Next, I'll be going over the backend converter updates. So these backend converters mainly deal with ONNX model format, translate them into a backend runtime framework where actual inference is run on the ONNX model. And for these backend converters, I'll be going over the ONNX TensorRT as well as the ONNX TensorFlow converter. Next up, I'll be going over the roadmap for the converter SIG. And finally, there'll be a get involved slide for those of you that wish to participate in the converter SIG anytime after this meeting. So the first converter I'd like to go over is the PyTorch to ONNX converter. So the latest release that will be coming out very soon is PyTorch version 1.12, which supports ONNX exports up to ONNX offset 16. So there has been a bunch of new features added in this release, and some of the highlights include the ability to export neural network modules specifically as ONNX local functions, and this allows specific backends to target these functions specifically for accelerated inference. There has also been a lot of new ops support. You can see the full list listed there. And we've also added the ability to export ONNX bflow16 and optional data types, as well as added support for exporting quantized models, along with exporting models trained in mixed precision with Apex02. So for any users that are working with these new data types or working with quantized or mixed precision models, we recommend you to try out the new PyTorch exporter and see the updated workflow into converting to ONNX. Finally, we've added support for A10 fallback for non-Caffe2 backend, and any user could see the full list of A10 supported operators in our documentation online. Finally, if this piqued your interest, we have a separate talk by Bowen later today at 1:35 p.m. where he will go a little bit more in depth about all of the changes we've made in PyTorch 1.12. Next up is the TensorFlow to ONNX converter, and the latest release here is TF to ONNX version 1.11.1, which supports exporting to ONNX in offset 16 and TensorFlow versions up to TensorFlow 2.8. So the highlights here is that the default offset export version has been updated to 13, and there are a few new ops that are now able to be exported, including TF-lite batch matmul, TF-lite matmul, tensor scatter add, and random int. In addition, we've improved model export for Q2Q model, as well as general improvements for export for models trained in TF-lite. So again, if you're using Q2Q models or if you're using TF-lite, we recommend checking out the latest release for the updated workflow into exporting to ONNX. Next up is the sklearn to ONNX converter. So the latest release here is sklearn to ONNX 1.11.2, which supports ONNX export up to offset 15. The highlights here is that we've added a new up support for SGD1 class SVM. We have also a bunch of bug fixes for previously supported ops, as well as improved library import performance across the board. So we recommend users to update to the latest version for improved user experience when converting sklearn models into ONNX. Next up, I'll be going over the backend converters. So the first up is ONNX to TensorRT. So the latest release here is ONNX TensorRT 8.4, and we support importing ONNX models up to offset 17. There are two new ops added in this release. So now we can import models using shrink and XOR, and there has been improved support for and bug fixes for these following ops: argmax, argmin, range, celu, gem, and einsum. Finally, we've improved support for dynamically shaped models, and we have general performance improvements across the board. So we recommend any new users and recurring users to upgrade to TensorRT 8.4 and start benchmarking with TensorRT to see what sort of performance improvements you could get when running ONNX models. Next up is ONNX TensorFlow, and the latest release here is version 1.10, which supports importing ONNX models up to offset 15 and supports TensorFlow versions up to 2.8. For new ops support, ONNX to TensorFlow actually supports the entire offset 15 ops spec, at least partially, as well as supporting ONNX optional data types. So again, for any users with models that are using offset 15 or lower and are using ONNX optional data types, we recommend using the latest version of ONNX and TensorFlow to import your models and do any new benchmarking there. As for the roadmap, the converter SIG had a few short-term and medium-term level goals. So for the short term, we wanted to improve our ONNX operator documentation support matrix across all the converters. And this has been done over the past year across all the converters. So this is a very good improvement. For the medium-term goals, there are two main things that we want to focus on. The one is setting a minimal offset support across all the converters. So there has been discussions that previous offsets should be deprecated, and we are working on formally proposing deprecating offsets less than 9 as a starting point, and we can move on with the offset deprecation in the future if this goes through. Secondly, the other medium-term goal we have is to improve community-driven tooling. We've seen across a lot of converter repos, as well as across different companies, there are a lot of ad hoc implementations for a bunch of utility tools, such as fuzz testing, shape and type inference for ONNX models, quantization tools, and constant folding across ONNX models. And we want to work together with the community, as well as the ARC Infra SIG group, to help start standardizing some of these tools and getting them contributed back into ONNX so that users and the converter users have have a one-stop shop for all of the utility functions that they may want to use. Finally, there is the perpetual goal across all converters to constantly improve, both in terms of bug fixes and improved operator and offset support. And for PyTorch specifically, one big item on the roadmap is that improved support for PyTorch models with lazy tensor and autograd functions are in the works. So definitely be on the outlook for that. So finally, feel free to get involved. So any quick feedback, feel free to join us on Slack in the ONNX Converters channel and drop by a quick comment or start a thread. For those that want to get involved a little bit more in depth, feel free to subscribe to our ONNX Converters SIG mailing list, where we send out invites for monthly meetings. So please subscribe if you want to get involved in that. And finally, we have a very amazing community across all the converter repos. Don't feel shy to open up issues or start discussions across GitHub, because we always welcome new contributions and new discussions, and we are very welcoming to any users that want to get involved in ONNX. So thank you. That concludes the ONNX Converter SIG for updates for today. Thank you all for listening.
Right. Thanks, Kevin. So I'm the new SIG lead of ONNX Model Zoo and tutorials. So today updates since that workshop, and I'm Jacky from Microsoft. So today I will, we have two parts. So first I will talk about ONNX Model Zoo and then ONNX tutorials. So yeah, so before I jump into details, so let me introduce ONNX, what is ONNX Model Zoo. So ONNX Model Zoo is a collection of pre-trained and state-of-the-art like machine learning or deep learning models, which were mostly contributed by ONNX community. And right now there are 40 kinds of ONNX models and 168 models in total with different kind of ONNX versions, including 35 vision-based ONNX models like image classification, object detection, super resolution, and also there's 5 models about machine comprehension like BERT, GPT-2. So yeah, and for what is ONNX tutorial? So ONNX tutorial is a place that have a lot of documents, notebooks demonstrating how ONNX in practice for different kinds of scenarios like different framework platforms and how they can work with different kinds of device types. Yeah, so I'll talk more details about ONNX Model Zoo first. So we have a lot of new quantized models, which is mainly contributed by Intel. Thanks mainly from Intel, she contribute a lot of integer 8 models in ONNX Model Zoo, and including like both vision-based and text-based models. And one thing I want to highlight is that so we improved the test coverage at this moment. Like we have a routine CI in ONNX repo, like keep running the latest ONNX checker and ONNX JPinference with old Model Zoo models. And like right now, like all of them are passed. And there's only some ancient models which is still using upset 3, so they don't have the shaping bins function, so we cannot verify in ONNX. Otherwise, they are all passed by the latest release, ONNX 1.12. And next, one thing I would like to highlight is that recently we fixed a lot of broken test data set in ONNX Model Zoo. So right now that we have verified that all the models, most of the ONNX Model Zoo models can pass ONNX runtime with CPU per byte, and there's only one model failed. Then let me summarize what we did for the improvements since that workshop. So we did a lot of CI improvements because we introduced more quantized models. So we need to make the CI to take the right machines to run the test for quantized models. And as I mentioned in the last slide, we fixed a lot of broken test data set. And also we collaborate with Hugging Face team that we like accomplish a Gradle app, which is a Python web app to demo machine learning models, and I'll show you in the next slide. So Gradle is a web interface, and then we like host ONNX Model Zoo models in Hugging Face space, and then we use ONNX runtime as backend engine to inference the accurate result, and then finally it will show a great result on the web. So meanwhile, for ONNX Model Zoo, like we can also like have a link to redirect like certain ONNX Model Zoo models to Hugging Face space, and you can show some demo there. And they have a tutorial like how to do it in their Gradle website. And in Microsoft, we also I have also just published a blog in our Microsoft open source cloud blog. Next slide, please. So here I will show a quick demo to you. Could you? Yeah. So like as you can see, it's a website. So after we run some easy Python code, we can just upload some image on the left. And from the right, you can very easily, okay, the website will tell me, okay, there's a typecast there. And the only thing we need to do, just write like a couple of easy Python code here, like do some image processing, and then just feed the image to ONNX runtime, and ONNX runtime will inference the output result for us. And the Gradle will show the result on the web. And also they provide some community functions that you can make a pull request or start discussions about this app. Next slide, please. Yeah, thanks. So talk about some roadmap about Zoo. So like Kevin mentioned in his slide, we want those like upset 3 models because they even cannot be run by ORT and they don't have shaping function in ONNX. And also we will keep improving our CIs to verify ONNX Model Zoo models. And also we like looking for more models contributions, including quantized models, and perhaps currently there's no training example models there, but I think we can like have a first training example models in the future. Yeah, then I will talk about ONNX tutorials. So yeah, for ONNX tutorials, mainly we we finally introduced the CI there because there are a lot of deprecated URLs. So like right now, if you publish a new notebook or document there, we will in the CI it will automatically it will validate the URLs for new PRs, and also that we are weekly to go through the whole repos to check all URLs there, just in case that some URL is deprecated. And also we run some Python formatters to clean the notebook. And yeah, for the roadmap, I think here is just we want to keep polish the old tutorials, and in the future, I think we will prefer like URL redirections to other tutorials. Okay, yeah. So that's why I want to like say welcome to contribute, and actually the contribution of the new ONNX model is quite easy. Like you can first get the ONNX model, like it can be produced by any converter, and then you can use OR the test data set, including input output, and then just write README and pass the CI by ONNX run by ORT inference with CPU and get the right result, then your PR is ready to go. So yeah, if you have any topics you want to bring up, feel free to join us on Slack. There's a channel called like ONNX Model Zoo, and please help us to review the PRs. There are a few opening, and most importantly, I was looking for more volunteer approvers for SIG model tutorials. I think it's a very good opportunity for you to be visible to ONNX community, and also it's a good chance for you to learn ONNX model, and ORT. Yeah, that's all I have. Thanks.
Hi, my name is Joaquin Anton, and I would like to share with you what we've been working on lately in the ONNX preprocessing working group. Let me recap what the goal of the group is, and then I'll show you the work we've been doing lately. Today, ONNX models typically expect the input data to be already preprocessed. The complexity of that preprocessing pipeline may vary depending on the application. For instance, some typical steps in a computer vision application are cropping, resizing, normalizing, and transposing to a planar layout. Those preprocessing steps are usually defined vaguely or expressed in Python with some particular processing library. This lack of standardization creates a problem. Different data processing toolkits can have different definitions of apparently the same operation. In this example, we are comparing an image resize operation for two popular libraries, Pillow and OpenCV. As you can see, the results are obviously different. It all boils down to the fact that Pillow applies an anti-aliasing filter when downscaling, while OpenCV does not. Sometimes, small differences in the data preprocessing pipeline used during training and inference can result in a drop of accuracy. The second obvious problem with the current approach is the lack of availability of the libraries on the platform we are deploying. The goal of the group is to standardize the definition of those data preprocessing operations so that they are not ambiguous, and include those in the ONNX model. This simplifies deployment and avoids the potential accuracy problems we mentioned. Since the group was created, we've been working on different topics that will help us reach our goal. Some of the work is related to the general infrastructure that will allow us to include the data preprocessing in the model, such as being able to combine preprocessing pipelines with existing models, or being able to batch process samples, as we typically do at the preprocessing stage. Another line of work is related to the extension and creation of operators to enable our first end-to-end model, which we chose to be ResNet 50. Let's look at those items more closely. We proposed a set of composition utils that allow the user to merge two models or graphs by connecting some of the outputs in the first model to some of the inputs in the second model. The user can also decide to add a prefix to all the names in a given model to avoid name collisions when merging. The second topic was batch processing. A typical case when doing data preprocessing is to have a batch of samples that are not uniform in shape. In ONNX, we can represent that as a sequence of tensors. We do want to process each of the samples by applying a series of preprocessing steps. The typical result is a batch of samples that are now uniform in shape. Before feeding the network, we concatenate all those samples to a single tensor. To enable this pattern, we propose the sequence map operator. Sequence map is a generic sequence processing operator that can apply a graph to each element in an input sequence, producing a sequence as an output. We can use sequence map to apply our preprocessing graph defined on a one-sample basis to a batch of samples. Also, we are currently investigating ways to tag the preprocessing part of the model, so it can be later identified by backends. The current approach is to use a model local function as a single entry point for the preprocessing subgraph and mark it as such via metadata properties. To enable our first example, ResNet50, we are proposing a couple of extensions to the resize operator. The first one is an optional anti-aliasing filter to be applied when downscaling the input. This is necessary to match the behavior of some popular image processing libraries such as Pillow. The second extension is a keep aspect ratio policy that changes the interpretation of the target size. The policy can be to stretch, ignoring the original aspect ratio, which is currently the default behavior. Or it can be to treat the target size as either a maximum or a minimum size while keeping the original aspect ratio. The other operator we need for our first example is a center crop or pad operation. The operator we are proposing offers a convenient higher level abstraction, and it's implemented as a function that relies on the existing pad and slice operators. And that's all from us. We encourage you to join us on our Slack channel and our monthly meetings and share your ideas. Thank you for listening.